So we can start also today with the lecture of the 5th of May 2020. And we must continue to talk about the statistical analysis, in particular aimed to define the design load. Indeed, up to now, we have talked about the design loads. In particular, in terms of either the water discharge or the wave height. So we can use the star symbol in order to indicate the value of the design load. And the design load is actually defined with respect to the value of the so-called return period that is related to the probability, or better, to the non-exceedance probability of the values of the design load. Actually, yesterday we finished the lecture by saying that we cannot directly perform the statistical analysis on the basis of the observed value of water discharge, this one, water discharge, and also based on the observation of wave height. So it seems that the tools that we described so far cannot be applied in real application. Indeed, what we have done, we started from the selection of the return period. This is the first step, depending on the safety related to the kind of hydraulic structure that we are designing. Then we used observations in order to estimate the parameters estimation. And when I talk about parameters, I'm talking about the parameters of the cumulative distribution function, in particular in this case of the generalized extreme value distribution. And then the definition, or better, the estimation of the design load. That is basically or the water discharge or the wave height. Indeed, we need the water discharge in order to design hydraulic structure, say it a well, say it dam, say it the verification, the hydraulic analysis of channel, either small or large channels, natural rivers, and so on. On the other hand, we need the design load in terms of wave height when we are called to design maritime structure. Now, the problem is that all these analyses are based on the availability of observations. Indeed, we said that in order to evaluate the design load for given return period when the return period is more or less several as an order of magnitude, as the value of several years, say it 100 years, just for example. In this case, we need a long enough time series of observation in order to have to get a reliable estimation of the design load. So the first aspect is that observation must be long enough. But on the other hand, we need also to talk about the homogeneity of the sample. In this, by means of these words, it is rather unclear what I mean when I say that the sample must be homogeneous. Indeed, if we talk about in general of the approach that we are using, if this is the set representing the population of the stochastic variable, we said that our sample is a subset of this population. So this is the sample. So the sample is characterized by two main features. The first one is that it is smaller than the population. So the sample is a series of realizations extracted from the population. But on the other hand, the sample is made of a series of realizations of the same stochastic variable. Indeed, we can have also another stochastic variable, population of stochastic variable. So in the reality, in the real world, if this is the sample, most of the realizations may come from one stochastic variable, but some of them, at least a very few, can come from another stochastic variable. So in this case, we need to perform the statistical analysis only if the sample is extracted from the population of the same stochastic variable. When I talk about the extraction from the same stochastic variable, I'm talking about the homogeneity of the sample. So the sample must be composed by homogeneous realizations. I can show you, I can describe you a kind of an example. For sure, you know that in some places in the world, hurricanes can occur. Hurricanes, I tornado, gli uragani. Then it is rather simple to understand that if we take into account, just for example, the rainfall in places where hurricanes occur, actually we have two stochastic variables. The first one is the rainfall related to hurricanes. And also we can have another stochastic variable, rainfall, related to the occurrence of the normal storms. Then if we collect data by means of a kind of sensor located within this place, we can have in general a sample in which some measurements are extracted from the rainfall related to hurricanes. Some other are extracted from the rainfall related to normal storm. So we need, first of all, to separate the sample and to perform two different statistical analyses. Statistical analysis 1 and statistical analysis 2. So The real problem is that the statistical analysis must be performed by using a sample made of realizations of the same stochastic variable. And to be honest, this is a really difficult and complex operation. So it is not so simple to separate the realizations of coming from one stochastic variable from the realizations of another stochastic variable. So in general, we need to analyze the problem by looking also at the phenomena related to the realizations of the stochastic variable. Indeed, in this case, in this example, it is quite simple to understand when an alkane is occurring, and then to separate the realizations that compose this sample. Now, why we are talking about alkanes or normal storm? Indeed, when we talk about the water discharge time series, actually the time series can be long enough. It is true that we have a long series of measurements, at least in some places in the world, but we can have the measurements of water discharge. So the problem is not related to the duration of the observations, but it is related to the fact that the sample in terms of water discharge are not homogeneous. Indeed, from a physical point of view, the water discharge, let's try to depict a river. So this is a river. Why, if we take into account a section of the river, we have a water discharge flowing through this section? And then why we can measure this water discharge? Actually, because it rains. This is quite simple to understand. The rainfall is the physical phenomenon related to the existence of the water discharge. So if it rains, the water discharge increases. If it does not rain, the water discharge is low. Then, from a physical point of view, we have a kind of basin, and depict it in this way. So a portion of the land that is called watershed that collect the water coming from the sky. So in this case, the water comes into this watershed. Then the feature of the rivers, the largest one, but also the smaller one. So we have a series of rivers, small, high or small. Then if it rains, the water comes into these rivers and then flows up to this section. So actually we have the rainfall on one end and the so-called runoff on the other hand. So this is actually the runoff. In reality, only a portion of the water related to the rainfall is transformed in runoff. So not all the water coming from the sky is transformed in runoff. Indeed, in the middle, we have the watershed. Why some of the water coming related to the rainfall is not transformed in runoff? Just for example, I can make a simple example by inviting you to pay attention to the fact that the water can infiltrate into the soil. So if you have a natural land, the water before to starting to flow on the land, it can infiltrate into the land, into the soil. So only a part of the rainfall is transformed in runoff. So this transformation, I mean the transformation of the rainfall into runoff, depends on the watershed features. I mean, if I have a lot of impervious area, impervious is impermeabile, such as an example, a lot of roads, a lot of urban areas, a large portion of the rainfall is transformed in runoff. When instead the watershed is made of a large portion of natural land, a large portion of the rainfall infiltrates into the soil, and then only a small portion of the rainfall is transformed in runoff. So the transformation from rainfall to runoff depends on the watershed features, in particular on the using of the land use related to the watershed. And as you can understand, the watershed is changing. So where a long time ago there was a natural land, perhaps today there is a urban area. So the features of the watershed is changing. Then I mean that the transformation from the rainfall to the runoff is changing too. So if I perform the analysis directly on the runoff, actually I'm analyzing the results of a phenomenon that is not the same. So if I have, even if I am a long time series of water discharge measurements, actually those measurements are not extracted by the same stochastic variable, because during the time the features of the watershed has changed. Then in this case the element, so the realizations that compose the sample are not extracted by the same stochastic variable. Then we cannot perform the statistical analysis directly on the time series. I switch to Italian just a little bit. Quindi il vero problema relativo all'analisi statistica estremale delle portate non è tanto il fatto che non abbiamo delle serie lunghe, perché in realtà, magari non è una verità generale, però in realtà possiamo avere a disposizione delle serie anche abbastanza lunghe. Sempre ci sono dei fiumi nel territorio italiano che sono monitorati da tantissimo tempo, dagli anni 30, quindi abbiamo delle serie temporali che raggiungono anche i 90 anni. Se vi ricordate quello che vi ho detto ieri, che possiamo utilizzare un tempo di ritorno circa pari al doppio, il triplo della lunghezza delle osservazioni, capite che possiamo arrivare a stimare anche in maniera affidabile carichi di progetto con tempi di ritorno fino a 200-300 anni, quindi tempi di ritorno di tutto rispetto. Il problema è di tipo fisico, perché rispetto a 90 anni fa il deflusso, che è il risultato di una trasformazione dell'afflusso, cioè della pioggia, in realtà è cambiato nel tempo. Laddove 90 anni fa c'era un territorio, diciamo, poco antropizzato, oggi invece larghe porzioni del territorio potrebbero in linea di principio essere state trasformate. In questo caso non tutta, o meglio, la porzione di acqua che cade dal cielo perché piove, che viene trasformata in deflusso, può cambiare, e in maniera del tutto intuitiva. Se pensate a dell'acqua che cade su una strada oppure dell'acqua che cade su un campo incolto, capite che la porzione di acqua che si trasforma in deflusso è totalmente diversa. Quindi, siccome questa trasformazione tra la pioggia e la portata dipende dalle caratteristiche del bacino idrografico, watershed, e se E visto che le caratteristiche del bacino idrografico cambiano nel tempo, in realtà cambia anche la portata. Quindi concettualmente è come se io stessi parlando di un campione anche molto lungo, quindi statisticamente rappresentativo, che è però costituito da elementi che sono estratti da variabili aleatorie diverse. E quindi, nella sostanza, non sono autorizzato a fare l'analisi statistica estremale direttamente su quella serie. Another problem is related to the wave height. When we talk about the wave height, actually, we have not long time series are not available, are not available. So we have another kind of problem. In this case, I mean in the case of the design of maritime structure, the problem is related that we started to measure wave heights starting from the end of the 80. So we have about 30 years of observation. So in this case, the problem is not related to the homogeneity of the samples, but to the duration of the time series. So we need to solve the two problems in two different ways. Here, we need to understand, we need to try to understand the phenomenon related to the rainfall. Then we need to understand how the rainfall is transformed in runoff. And then again, we need, of course, this aspect is related to the feature of the watershed. And also there is a needed problem, a third problem, that is related to the temporal variation of the design load within, of course, the same variation of the hydraulic load, of course, within the frame of the same extreme event. So we need to tackle the problem of the rainfall, to tackle the problem of the transformation of the rainfall to a runoff, and then we need to try to understand the temporal variation of the design load. So we need to tackle a series of problems. In this second case, we need to understand if this problem, I mean the problem that long time series are not available, can be solved by using another kind of statistical analysis. Indeed, in this case, we will perform another kind of statistical analysis that is related to the extreme event definition that will be extracted not by means of the maximum blocks, but by means of the peak over threshold method. So when the wave height exceeds a given threshold. So we need to start, first of all, by talking about rainfall. Today, we need to talk about the phenomenon of the rainfall, because we will try to transform the rainfall to a runoff, and pay attention that we are interested in the runoff, the water discharge, not directly in the rainfall. We must refer to the rainfall just because we have not homogeneous observations of water discharge. Whilst in terms of rainfall, we have the approach is exactly the same. We start from a return period. We use observations to estimate parameters, and then we evaluate the hydraulic load in terms of H, hydraulic load, in terms of the so-called rainfall depth. Italian is altezza di pioggia. So we switch the problem from starting from the return period with the aim to estimate an hydraulic load in terms of water discharge. We switch to another problem. We again start from the return period, but the aim is to estimate the rainfall depth. Now we need to understand what we intend for rainfall depth. So H is a kind, you can imagine, a kind of sensor that is made of a box in which if it rains, the box will be filled with water. Then we can imagine to weight the box in order to have an estimation of the volume of water that is collected during the time by means of this box. So if we know the area of this box, we can define a kind of rainfall depth for unit area. So if this one is 1 square meter, the rainfall depth is the depth of the water volume that fill a box with a unit square area. Then during the time, I can try to get a kind of variation of the rainfall depth within this box along the time. So when it does not rain, I have not variation of the rainfall depth. When we have an event, I can define a kind of time resolution during which the box is able to collect a certain value of rainfall depth. Then it continues to rain, and then the event finished. So, and then the event finished. This duration that we can call Td is the duration of the event. Then it does not rain, and then a new event will occur. Then again it does not rain, and then another event. So it is really simple to understand that the rainfall depth is a function of the duration. So the rainfall depth is a function of the duration of the event. So we need to understand the formal shape of this function. Somebody has proposed to write the rainfall depth as a function of the duration. Pay attention, this is not the time, this is the duration of the event. Then somebody proposed to write the rainfall depth as a first term that is a parameter, this is a parameter, times the duration of the event, plus another parameter times the duration of the event, over another parameter plus the time duration, power m. This is a very general formal shape of the function that expresses the dependence of the rainfall depth from the duration of the event. Of course, the longer the event, the higher the rainfall depth, of course. So I mean, this relationship give us the total, so the total height, the total rainfall depth during an event for given duration. Now we can, if we come here, we can take, just for example, this event during which the rainfall depth is equal, say it H1, we can define a kind of average intensity. The average intensity that we can call I, that is of course a function of the duration, it can be obtained as the total rainfall depth during an event over the duration. So if we use this relationship, we can say that we have IA plus A over B plus T T power n. So this is a kind of average intensity. So I repeat, when we take into account a given event, we can estimate the total rainfall depth, that is actually a kind of volume of water for unit area, and then we can define a kind of average intensity, defined as the ratio of the total rainfall depth during the event over the duration of the event. It can be observed that if the duration of the event is very large, so you can think to a very long rainfall event. In your experience, personal experience, you can guess that the average intensity, is rather small. Indeed, when the rainfall events are very long, the intensity, at least from your physical point of view, the intensity is not so large. Indeed, this relationship can be used for very large value of the time duration. Of course, the intensity, in this case, is equal to IA, this one, that is always a number, so the time duration does not influence this term. But in this case, we have a very large value of the time duration, of the duration of the event, and then this term is 0. So the average intensity for very long events is IA. So this parameter has a physical interpretation. It is the average intensity of a very long rainfall event. When the event duration is very small, in this case, the average intensity is this one, as Td is small if compared to B. Then also this term is a kind of measure of the increase of the average intensity when short rainfall events occurs. Indeed, also for your personal experience, if the events are very small, the intensity is really high. When the rainfall duration is small, the rain is heavy, so the intensity increases with respect to shorter events. Indeed, if we make a kind of plot of qualitative plot in which here we have the duration of the event, here we have the average intensity of the event, we can start here from this intensity. Here somewhere we have the intensity of the long events, and then the intensity decreases as the duration of the event increases. This is called usually the intensity duration curve. So in general, this relationship is able to describe the variation of the average intensity. Remember, the average intensity, not the instantaneous intensity. So the average intensity decreases as the time duration and as the duration of the event increases. I switch to Italian. Quindi nella sostanza quella formula ha un obiettivo ben preciso, che è quello di riprodurre quello che succede fisicamente. Per vostra esperienza personale sapete benissimo che quando le piogge sono molto lunghe l'intensità media è piccola. Quando invece le piogge sono piuttosto brevi, pensate ad un temporale estivo, l'intensità anche per vostra esperienza personale può essere intesa come un'intensità molto elevata. E quindi quella relazione che vi ho fatto vedere prima, cioè questa in questa lavagna, in realtà rispecchia piuttosto fedelmente questo comportamento. Now, we can observe that the intensity, or better, the average intensity for very long events is negligible, is almost zero. And also it is possible to give the value of the parameter b as 0. In this case, we have that the rainfall depth as a function of the duration, as a function of its duration, is equal to the parameter a, the duration td over the duration td power m, that is equal to a, the duration td 1 minus m. Then this is a number that we can call n. So in general, a simplified relationship giving us the rainfall depth as a function of the duration is a parameter times the independent variable power another parameter n. Now it can be observed that n must be lower than 1. Indeed, we know, if we look here, if we have this relationship, the intensity as a function of the duration is equal to T A Td power n minus 1. I mean h over the duration. So h is ATD power n over the duration minus 1. In this case, this plot is more or less this one. So for very small duration that has not any physical significance, we cannot say of an event of 0 duration. So in this case, the duration must be higher than a given limit that we can call this one. So here we can see that this relationship must describe that the average intensity decreases as the duration of the event increases. Then in this case, we can try to write the average intensity, that is this one. And we can try to estimate the variation of the average intensity with respect to the duration of the event. And of course, this must be lower than 0. Indeed, as the duration of the rainfall increases, the average intensity of the event decreases. So we can perform the derivative of this relationship with respect to this parameter. So we have n minus 1, a is a parameter, td n minus 2, but this is equal to a td power m over td squared, that is equal to n minus 1 the rainfall depth over the duration squared. This term is physically higher than 0. As we need to have that the derivative of the average intensity with respect to the time duration of the event must be lower than 0, this should be lower than 0. Then, if n minus 1 should be lower than 0, then n should be lower than 1. So, in the rainfall, in the relationship giving us the rainfall depth, the parameter n is a number lower than 1. Usually, the rainfall depth is expressed in millimeters and the duration is expressed in hours. Then the parameter A, that is expressed in millimeter, is the rainfall depth for 1 hour event. So if we take into account an event with only 1 hour duration, we can have an estimation of this parameter A. Now we have a problem. Indeed, the parameter A and the parameter n must be evaluated. We don't know the values of the parameter A and the parameter n. In order to estimate the parameter A and the parameter n, we can use the observations. So let's try. We can, in general, resort to the measurements of rainfall depth for given durations. So we have the rainfall depth for changing time. So when an event occurs, we have something like that. A really strong event, and so on. We can define a kind of cumulative rainfall depth. Pay attention, this is not the duration, but this is the time. So actually, we can write a kind of cumulative rainfall depth something like that. Okay? Then we can take into account the difference of the cumulate water rainfall depth for a given delta t. Then this is the difference. So this is the rainfall depth fallen in delta t. So it is possible to analyze the time series of rainfall depth in order to get directly the rainfall depth for given time duration. Pay attention that here in this plot, the approach was not to define a time duration, but to keep the duration of the event. In this case, we give the duration, delta t, and we try to understand, to estimate the rainfall depth for that given duration. So we have a series of rainfall depth for the same time, from the same duration. So just for example, we can have this value with this event, but we can have another value, if this is delta t again, for this event, H max. But also we can have another estimation for this other event. So we have a series of rainfall depth for given duration, and then we keep the maximum. So if we, just for example, this is 2019, the last year, for the time duration of delta t, we have the H max. So the rainfall depth, the maximum value of the rainfall depth for this given duration. We can keep a duration just, for example, of 1 hour, and we can repeat the analysis for different durations. So we have 3 hours, 6 hours, 12 hours, just as an example, 24 hours. So, very simple, we have H and we have TD. Pay attention. Now this is the duration. So we take these values. So this one, these two, this one, and this one, and we put on this plot. So we have the duration of 1 year, of 1 hour, the duration of 3 hours, the duration of 3 hours, the duration of 6 hours, and the duration of, it is 12 hours, and finally the duration of 24 hours. Then we can estimate the parameters of the power law, this one, H equal to ATDN. So we can use the observed values in order to get an estimation of A and N. Indeed, H equal to ATT power N can be transformed by using the logarithm plus N logarithm of the duration. And this is a line. Then again, as we have done for the statistical analysis, we can write a reference frame in which we put the logarithm of rainfall depth, the logarithm of the rainfall duration. We can have a series of observation. This is the line, this is the slope, and this is the logarithm of A. If we call this as a capital A is equal to the exponential of A. This line may be computed by means of a least square method. So we have seen that in general the observations can be used to estimate the parameters of the rainfall depth relationship. Of course, we can also write this relationship in terms of average intensity, but we are missing something because we don't know the exceedance probability of this rainfall. So we need to perform further analysis in order to associate, to relate to this rainfall also its exceedance probability.